step by step. Learn more about how these transformers are actually being applied as language models and in other applications as well. So we're going to break down the core concept of attention really step by step. All right. Let's do that. Okay. Attention itself is a very informative word, right? What it means is we have this inherent ability as humans to think about an input and automatically zoom in and pick out the things that are salient, the important features. So let's build up our intuition starting with an image. How do we figure out what's important in this image? One way we could do it, naively, is we could go pixel by pixel, left to right, back and forth, and scan this to try to compute some value about how important these individual pixels are. But of course, our brains don't operate like that. We're able to automatically look at this and pick out and attend to the important parts. And the first part of this problem is this notion of being able to identify which parts are important in some input. And then ultimately, we want to use that identification to extract the features, the components of the input that correspond to these high attention values, right? And to think about this more concretely, this notion of identifying the parts to attend to is really similar to search, right? So when we do something like a search, we present a question and we're trying to seek an answer. Let's say you came to this class, right? And you had the question, how can I learn more about neural networks and deep learning and AI? Maybe one thing you could do besides coming to this class would be to go to the internet, have all the videos, all the materials available on the internet, and try to do a search to find something that matches your query. Let's say you go to a giant video database like YouTube, and you put in your query, your ask, deep learning. That's your search topic. And now what search does is let's say we go through every video in this database, and we extract some informative nugget of information, a key, that represents the core element of that video, a descriptor of that video. And now we have our query, and we have a set of keys. Now our task is, okay, to actually do the search. How could I go about this? Well, I want to see how close the match is between my query, what I searched for, and those keys, those key indicators in the database. And I want to see how similar they are. So I'll do this step by step. Ask, how similar is my query to these keys? First instance, a beautiful video about elegant sea turtles, not similar. A video from our past lecture on deep learning, yes, similar. A key related to Kobe Bryant's fadeaway, not similar. So now we've identified the key that's important. We want to attend to this. Our last task is to actually extract the value that's associated with this similar match that we found. We want to extract the features that we want to pay attention to, the video itself, and we'll call this the value. And because our search was implemented with a good attention mechanism, we've identified the best deep learning course out there for you and your query. This concept is really the core intuition behind attention. And that's very, very closely related to how this attention operation works in neural networks like transformers. So now let's go back to our sequence modeling problem, where we have a series of words and we want to predict the next word with this sentence. If we break this down step by step, first remember, we don't want to process this information time step by time step. We've broken down that need for recurrence. We're going to feed in the data all at once, and still we need a way to encode some notion about order. So what we're going to do is we're going to put in an embedding called a positional embedding that effectively gives us a way to encapsulate that relative position of these elements in that sequence. We're not going to go into great detail about positional embeddings, but you can think of it as an encoding that gives us some representation of position in the sequence. Now, we take those position-aware encodings, and we do that search operation, and we operationalize that search operation to extract 3 sets of matrices that we call the query, the key, and the value, just like I introduced before. The way we do that is we take the positional embedding and think about that as representing our sequence in a positionally aware way. And we use a neural network layer to produce each of these individual matrices, the query, the key, and the value. The important thing to keep in mind is that it's that same positional embedding that's repeated in this mechanism of self-attention, but these are different neural network layers that yield different values for each of the query, key, and value matrices. That means is that they can effectively capture different information, as we'll see. Now, again, our next step in the search operation was to figure out, okay, how similar is the query to the key? And that's exactly what we're going to do next with attention. To do that, right, remember these are numeric vectors or matrices. And so we need a mathematical way to compute that similarity between 2 sets of numerical features. So let's say we have 2 vectors, our query vector, our key vector. And what we can do mathematically using linear algebra is measure the similarity of those vectors in space using the dot product. That tells us how close they are to each other. We can scale it, and this gives us a very concrete similarity metric that captures that similarity between the query and the key. That same principle can apply now to matrices as well. Dot product and scaling, that gives us a similarity metric. Now, let's think about what this similarity computation actually means. Remember, right, we're trying to understand how these components of the input relate to each other. What parts of the sentence are important to each other and important to convey the semantic meaning of the sentence as a whole. So if we have this example, he tossed the tennis ball to serve, let's say we've computed our query and key matrices, applied a scaling. We can then apply a function called a softmax to basically squish these values between 0 and 1. And now this gives us a matrix that gives us a relative weighting of how those individual components in the sequence relate to one another. Intuitively, you can think about things that are more similar as having higher attention weights, more related as having higher attention weights, things that are less related as having lower attention weights. So here, right, in this example, tossed and ball have a high score, tennis and ball have a high score, and so on. This gives us our attention weighting or our attention matrix. The final step is to now use that relative weighting to actually pull out those important features that we care about. What we do here is we take our value matrix, multiply it by our attention weight, and this gives us an output of a feature set over that input space that reflects the relative elements of the sequence that are interrelated relative to each other. That's really the core of how attention works. And that's really beautiful and striking to me because this mechanism gives us a very natural way to pull out and attend to features that are quite important relative to each other in an input. And architecturally, now, how do we actually build this out into something like a transformer? Well, one second, please. We can go, again, by taking our input, computing these positional encodings. We define these neural network layers that compute the query, key, and value. Then we can compute this relative weighting between the query and the key. That's a matrix multiply representing the dot product, a scaling, and a softmax, and then use the value matrix to extract features that have high attention scores. And these are the core operations that now define these attention heads, which are really the core component of architectures like the transformer. So as we've mentioned and realized, right, this is really the foundational, attention is the foundational building block of transformers. And as I think kind of some questions got to as well, right, a transformer architecture does not need to be defined by just a single attention block. You can actually stack multiple attention heads together to now be able to basically increase the capacity of your network and pull out different sets of features and more complex sets of features. So again, in this very intuitive example, maybe you have a network that has 3 attention heads, and if you go in and inspect, again, this is an intuitive example. Let's say you were to go in and inspect the values of each of these attention heads, maybe you could get some interpretability out with respect to the different features or parts of the input that the network was attending to. So what are some real-world use cases, and what has attention really enabled and transformed over the recent years? It's not only in language processing that transformers and self-attention have really led to tremendous advances. While that's the case, right, the mechanism and the architecture behind attention and transformers is very generalizable. And so as you'll see, right, natural language is one tremendous area that transformers have really taken off, and you'll get hands-on experience with this, not only in the lectures, but in a brand new software lab on LLMs. We'll also see a bit about how attention and sequence modeling has been extended to biological sequences in one of our guest lectures, and in fact, in something that may not appear sequential, like images or computer vision, there are a class of models called vision transformers that have now also become very, very powerful in processing image data as well. So to summarize and close, hopefully you've gotten a sense of how rich sequence modeling is as a set of problems and things we can consider. We saw